So, hello guys, we are gonna solve a set of 10 questions purely based on binary search trees. As this series, I am preparing for my GATE examination. So, I'll be sharing my insights and what I will be doing in the content creation sector. So, first, we'll consider this question. So what it is asking is to insert these elements. First, let's understand the question. Okay, and then delete the 50 using in order predecessor. So first, let's construct the tree. 50, then 30, then 70, 20, 40. Here it will come 60, 80, greater than 30, less than 40, 35, 45, and 65. Okay, if I have construct the tree, now we have to delete the 50, which is the root node using in-order predecessor. So, quick recap, in-order predecessor is something which is found in your left subtree and considered as the greatest element or the rightmost element or the node, whatever you call it, from the left subtree. So the greatest element from the left subtree is 45. Now what we do to this 45 is we completely delete this from here. We delete that. We delete that and replace the value of root with which value we have deleted. So this will be deleted. There will be no right child for 40. Okay. So now, which node replaces 50? Which node did 45? So the answer for this question will be 45. And which node is actually deleted? So this may sound a little bit tricky. In the question they give delete 50, but actually what got deleted is 45. What are you saying, bro? I can see 45 right here. But this value I used for replacing 50, but actually which value got deleted from here? 50 didn't get deleted. Of course it did, but we are replacing a value of 50 with something else. The node 50 is not deleted. The value on the node, this node is not deleted. The value in this node is deleted, and we are replacing that value with something else. We don't know what it is. I mean, we know of course, but if we consider this node is completely wiped off. So now we have the answer for this question, which node is actually deleted. It is 45th node. The node 45 is deleted. The complete node is deleted, not just the value in it. So now what is the left child of neuron? Of course, it is same, 30. So these are our three required answers. Now moving on to the next question. A search file 55 visits. So there is an element named 55, it seems. So we have, this is the traversal order. I'm sorry. This is the traversal order they have given, and we have to tell whether this can happen in a binary search tree or not. So let's consider. So we have came while traversing, we have came to a node named 40, and as 40 is less than 55 and 55 is greater than 40, we have to traverse towards the right of 40. So we found 70. Yes, it is possible to find, as it is 70 is greater than 40. Now as 55 is lesser than 70, we have to go to the right side of, sorry, left side of 70. So what we have next? 60. Yes, 60 can be uh, found in left side of 70. Then 60 is still greater than 55. Hence we go further left. We found 50. Now we have not given the further order, but that is not required for now. What did he ask? Can this happen in a BST? Until what he have given, yes, it will definitely happen. So I would like to consider another case. So let's consider instead of this 50, I have, I'll wipe off this and write 65. And if I have a note 65 like this, then this will become impossible. Why? Because 60 is greater than 55, and for finding 55 we have to go to the left side of 60, so I have to traverse on this side, but in the traversal order I don't have any element that satisfies the condition, that doesn't cannot be found in left side because it is a BST. So instead they give 65, but 65 is found in the right side. So this means that in this tree there is no element called 55 and it is impossible to search that element. So the option will be no if the order is like this. I hope you are clear with the concept. So further moving next, which insertion order cannot produce the BST below. So we need not to construct a tree for this one, or this one. We don't need to construct a tree for all this. I'll tell you a small trick. So as you can see here, we are finding here 20 and 60, right? So just in this order, uh, see that whether this comes before this or this and this comes before this and this, that's it. See, the root is 40, so first element will be 40 here. As you can see, the first element is 40 in the all cases, right? So we have equal percentage in all options. Now let's consider first option. Is 20 before 10 and 30? Yes, this is correct. Here 60 before 50, and we have to check here also. 60 before 50 and 70, yes, it is also correct. 60 before 50 and 70, yes. 20 before 10 and 30, yes, so this is also correct. 20 before 30 and 10, yes, of course. See, the order doesn't matter when it is, whether it is 10 or 30. See, if there is 20 and then I give 30 and then I give 10, and here when I have 20, then I give 10 and then I give 30. Doesn't matter. It becomes the same tree again and again. So after that, let's consider this tree. Yeah. So this is also done. And next coming to the D. 10 came before 30 and 20. This is a problem now. Why? Because it comes like this 10, 30, 20. But our tree is not like that. Even though this condition satisfies, this does not satisfy. Here also this condition is satisfied. 60, 70 and 50. As same as this. So the correct option is option D. Because they are asked cannot produce the binary search tree below. Okay. Next. Find the successor of 40 and predecessor of 60. So let us recap quick. If 40 has something like 60, no, it cannot have 60 because it is 50. Let's consider 40 have something like 45. Then the successor of 40 will be 45. That's it. As simple as that. But if there is no right subtree, but they are still asking for a successor. So there are two validations. For successor, the parents parent must be a left node of some node, and this some node will be the successor. For example, let's consider this example. 40. So is 40 a left node of 30? No. Hence this is not successor. Now go up. Now consider 30. Is 30 a left node of something else? Yes, it's left node of 50. Hence consider this. Now the successor of 40 is 50, because The successor rule, parent must see. To simplify this, we can write as at each level this goes up and it compares itself with the root and checks that whether it is a left node or not in case of a successor. Now we'll consider in case of a predecessor. So 60 has a right child but not has a left child. So we have to consider whether we have to consider something which is of right child of a parent. So this is the predecessor rule, right child of a parent, and that parent becomes your predecessor. Now see, uh we are considering 60 now. So 60 is 60 a right child of 70? No, it is a left child. So 70 cannot be the predecessor of this. Now we shift 60 up here. Now is 60, I mean we can consider like this also. We can check whether 70 is of something, or we move up 60 and compare 60 with 50 whether it is a right child of it or not. Now it is a right child. So the answer for this is also 50. Now let us consider some cases. If if I have something like this, let us consider uh, I'll take some space. Let us consider 20, uh, 40 and 10. No, I'll take another. Let's take something 30, 25, 35, 36 maybe. So even if we consider this case, if I have something like 25 and 20, sorry, I cannot have 25. Yeah, what happened? If I have 31 and that is mean 38 and 37 here, I'll make it neat. 38, 31, 37. If I have something like this, I can consider this as my successor because uh, it is begin. So but you have said that previously it has to be left of something, right? So there are two rules, rule 1 and rule 2. Rule 1 is if you have a right child, then successor is that right child. Rule 2, if you want to find a successor of a node n but you don't have a right child, then you have to apply this rule. You have to go up, compare whether the parent is a left child of another thing. I mean, compare with this if this is a left child of something, and then right. Okay, let's consider we have another node of 40 here. So now what happens is we does we does not get replaced with 40 now because we already have an intermediate 38 which we can replace this. Why? Because I mean this is not deletion, so we won't replace, but 38 will be the successor of 35 if there is no concept of 37. If 37 is there, 37 will be the uh, rightmost element, right? It is the right element of this node 35, hence it will be the successor. If there is no successor, we will go right here and make this as successor because the it moves up and it is the left node of something. So I hope this is a tricky concept, mostly asked in gate questions. I hope you understand. Next, moving to the fifth question. Exactly one tree is a valid BST. Let's check this one. 30, 20 is lesser than 30, 30 greater than 35, right? That 30, 20, 25 cannot be placed here. 20, this enters into the right part if and only if it is greater than 30. But 25 is not greater than 30. So we got our answer. Let's check other options too. 30, 30, 35. Hey bro, what the? Exactly one tree is a valid BST. Oh, we got our option. A. That's it. This will be also wrong option. Yeah, of course. A is our correct option. I didn't see the question properly. These are the mistakes you commonly make. Pre-order. Without constructing the whole tree, find the root. Yeah, of course. Root is this. Done. Root is 40. Left child of the root. Who? So, if I construct a tree, it will be 20. Of course, it will be 20. What the heck are you asking? Uh, it will be 20 because it's first. And then 30 will be going there. And 60. 60 is the first greater element. So right child of the thing is this and left child of 60. Of course 50. We got our answer. Let me write it properly. 40, 20, 60 and 50. Now let's verify this using constructing a tree for your understanding. 40, 20, 10, 30, 60, 50 and 70. The root is 40, done. Left child of root 20, done. Right child of root 60, done. And left child of 60 is 50, done. That's it. Just remember this. This is the lesser and the next element to the root, so it became the immediate left. And hence these are all lesser than 40, so these all will be inserted into left. And coming to 60, this is the first element which is coming after 40. As you know, pre-order is root, left and right. So this will be root and this will be the left, and this coming to this, it is uh, right because it is greater than 40. So it will be the rightmost, and after 60 there is 50. Now this will be the root. uh, to the 260, 50 will be at the right left because it is something that is, or what you can consider it, smaller. So coming to the seventh question, how many different BSTs can be formed using 5 distinct keys? So this is a cladding problem which can be solved using the formula 1 by n plus 1 2n cn. So 2n cn is nothing but 2n factorial by n factorial into 2n minus n factorial. So this is nothing but n. So we can rewrite this as n factorial whole square. But we have an n plus 1, and n plus 1 into n factorial becomes n plus 1 factorial. Didn't understand? Let's consider. Suppose there is 5 and there is 4 factorial. 5 into 4 factorial is 5 factorial, right? Because 5 factorial is nothing but 5 into 4 into 3 into 1. What is this all? This is 4 factorial. So I can consider 5 into 4 factorial as 5 factorial. Definitely. So this all will be gone, and we'll get a clean answer for this as 2n factorial divided by n factorial into n plus 1 factorial. So now we have n as 5. So 10 factorial divided by n 5 factorial into 6 factorial. So let's write, expand this, 10 into 9 into 8 into 7 into 6 factorial divided by 5 into 4 into 3 into 2 into 6 factorial. So we'll cut off this. 5 2s are 10, 4 2s are 8, 3 3s are 9. So we are left with 3 into 2 into 7, which is nothing but 6 sevens are 42. Answer is B. As simple as that. This is called as Clayton formula. Okay. Next, which statement is false? Okay. Uh, this is a true. That is a property. In order traversal of a BST sorted, whereas to case search complexity is order of n, every complete binary tree is a BST. What the? Let's consider a complete binary tree. So in a complete binary tree, there is no need of any order. I can insert here. This is a complete binary tree. It is not. It is easy to BST. No, complete binary tree asks if there is such levels, and I want to insert another level such that this level must start filling from left to right, and no matter about the elements in that level. See, I have one here, I can have two here and four here, but in a BST is this accepted? Definitely not. So the answer is C. This is false statement. Then searching for 45 visits. Okay, we are searching for an element name 45. Possible or impossible? Okay, we have reached 50, which is greater than 45, so we have to go lesser than 50. We found 30, which can be possible because we are searching for less elements, and 30 is less than 45, so search for right side. You found 40. 40 is still lesser than 45. You go like this and you came to 60. So as far of this is concerned, we can there is a still chance of finding 45 if there is a traversal like this 60 45. This is possible because if this is a tree, if we consider this as a tree, we can 50 is less. uh Wait a second. Wait, this is not possible, guys, because as you consider, it is 50, 30 is fine, 40 is fine, but 50, 60, it is not possible because it has to come here, right? It cannot come there. So this is impossible. So does that mean our first thing is also impossible? Let us consider that. I'm also human, I can make mistakes, but the important part is rectifying those mistakes. Yeah, this is fine. This is completely fine because see, we have 40, then 70, then 60, and 55 can be found in the right side of 40, and we are going through this 40, 70, 60, and then the question they gave 50. We can find even 50 here. There's nothing less than 40 that is found in this tree. So yeah, this can be considered. We did a good job. So now we are going to our last and final question for the session. So let's consider question number 10. Insert without drawing every insertion if possible. Bro, you are saying insert and then saying without drawing every insertion. Hide edges. And now let's choose to draw this. 50, 25, 75, 15, 35, 65, 85, 30, 40, 70. Okay. Height edges 1, 2, and 3. 1, 2, and 3. 1, 2, and 3. Yeah. The maximum is a 3. Number of leaves 1, 2, 3, 4, and 5. Number of leaves is 5. Successor of 40. Let's go. successor of 40. And there is also a shortcut. If you need to find a successor of 40 and it is the in order predecessor of the root, then you can directly replace that value with the root. 50 is the successor of 40. If you want to check with our rule 2, which is go up and up until you find something which is next to a parent. So is 35 left to 25? No. Go up. Is 25 left to 50? Yes. So your answer is 50. Here you go. Then predecessor of 65. So here we found a tricky one. So the greatest value in this is 85. So the answer cannot be 50. I mean, it can be or cannot be. Let's consider. Um, 65 is there. Let me redraw this part cleanly. 85, 65, and 70. Then predecessor of this, eh, it comes here and it becomes the right. Yeah, of course. Predecessor of this is also 50. Then delete 25 using a successor. Wow. So here comes the crazy part. Let us understand this part very clearly. 25, 15, 35, 40. The goal is to delete this. So in a left subtree, you but you need to do it with successor. Successor means you have to consider the right subtree. In the right subtree, whichever the element it is, if it is lesser than, then replace that. So guys, it is an in order successor for root 50. I'm very sorry. So this is the lesser value. Considering this, so we have to replace this. Sorry, we have to delete this and replace this. So I have deleted 35 node will replace. Which node is actually deleted? This is also 35. I hope you love this content. Although this is my day one, I have tried my level best to put it all my effort into this. So thank you for attending the session, guys.